We've covered the topic of space debris quite a bit here on the channel, and there have been a lot of ideas on how to deal with space debris: nets, tethers, lasers. But one idea is like straight out of science fiction, and that is a tractor beam. The idea is that you would have a spacecraft with an electron beam. It would fire electrons at a target, thereby charging up the target, and by removing electrons from the spacecraft, they would have opposite charges, and now the target spacecraft is attracted to the servicing spacecraft, and you could then tow your target around to some safer graveyard orbit if you're up in geostationary orbit. So this would be a way to mitigate future space debris using like Star Trek technology, which is always super cool. My guest today is Amy Haft. She is an aerospace engineer PhD student at CU Boulder, and she's a NASA Finest Fellow. She's working on this idea that would allow a spacecraft to drag defunct satellites into safer orbits without touching them, which is always such a scary and kind of dangerous process. So if you're interested in ways to mitigate space debris, check out this interview. Amy, I think we've been hearing from a lot of people that the challenge of space debris is just getting bigger and bigger. And we are launching, what are there, like 10,000 satellites now? People want to launch hundreds of thousands, millions of satellites. This problem is just going to get bigger and bigger. What is the sort of the landscape of the most feasible ways to remove this debris?
Well, that's a really great question in terms of what actually is feasible. I think that when it comes to space debris, the most important thing is like policy changes and making sure that people are complying with guidelines.
Right.
But
like, don't make the debris in the first place if you can.
Right.
Yeah.
Exactly. But, people have been launching stuff into space for decades and decades now. And, people weren't really sure what the consequences were going to be. And now we're getting to a point where we're starting to see some consequences. We're starting to have to avoid debris. And so in order to get rid of the debris that's there, especially from large objects, because large objects create smaller objects, which are harder to detect and harder to avoid, it's important to come up with safe ways to remove the objects. And I say safe because there's lots and lots of, different things that have been proposed, and all of them come with risks. So it's important to assess those risks and, before implementing them.
So when you talk about things that are safe, like shooting missiles at them to blow them up into smaller pieces of debris, I mean, these tests have been done. They're disastrous. We don't want to do that. But then ideas, nets, tethers, things to try and grab this material, you're putting your actual spacecraft at risk. And so what is the solution that you guys are working on?
So we're working on a contactless method of debris removal. And I stress contactless because all of the methods that use direct physical grappling come at the risk of breaking off pieces and creating more debris. And the smaller the debris, the harder it is to track, like I said before. And so by not actually grappling with the spacecraft, we are trying to mitigate that risk.
Yeah. That's interesting. Yeah, I never even sort of thought about that you've got I know the Japanese built a spacecraft that's designed to sort of get really close and eventually try to grapple with a satellite and try to bring it back down to Earth. But even just that process of trying to match its velocity, grapple with it, you may accidentally break off an antenna or who knows. And then now you've got more debris. And yeah, that problem just gets worse.
Yeah, the problem with debris is that it's non-cooperative and it's tumbling because it has no attitude control. And all the methods also have, ways of proposing to slow down the tumbling, but you still have to touch it. And so we're working on a almost sci-fi-like concept that allows us to reorbit debris without touching it. And so that way we don't even need to worry about detumbling it.
So explain how.
Yeah, so the concept is called the electrostatic tractor, and so we have two spacecraft. We have a servicer spacecraft, which is us, and then we have the target debris object, which is a large defunct satellite. And the way it works is the servicer spacecraft is equipped with an electron beam or an electron gun, and it shoots an electron beam at the target debris object. So the target is being bombarded with electrons, which causes it to charge negatively, whereas the servicer is emitting electrons, and so that's a negative current leaving the spacecraft, so it charges positively. So now we have a positively charged object and a negatively charged object, and that creates an electrostatic force between them that allows the servicer to then pull the target debris object out of orbit.
Wow. And how far away? I mean, I sort of think about the inverse square law. How far away do you have to be from your target for this force to actually be effective?
So when we do research, we are looking at around 10 meters apart, but we do most of our simulations in geosynchronous Earth orbit, which is GEO. Um, and the reason for that is because in space, there's a plasma everywhere, and plasma is charged particles that respond to magnetic fields. And as we get higher in space, the density of those particles decreases, which allows the electrostatic tractor to have more of an effect, like allows that electrostatic force to be felt over longer distances.
Right, right. But I guess if you're very carefully moving in space, then you could probably get within that 10 meters, 5 meters. Like it could be dangerous, but if you're very, very careful and move very, very slowly, you'll get to this place. So, okay, so you've now got a tractor beam on this this target spacecraft. Then what do you do?
Because we do most of our simulations in GEO, I'm saying reorbit rather than deorbit. And the difference is deorbit implies pulling the object into Earth's atmosphere and just fully getting rid of it. Whereas in GEO, we're so high up that it's not really economically feasible to bring it all the way back down to Earth. GEO is 6.6 Earth radii above the Earth's surface, so it's very high. And so rather than pull it all the way back down to Earth, we raise the altitude about 300 kilometers following guidelines into what's called a graveyard orbit. So the servicer is equipped with a thruster, and then it's able to slowly pull the debris object into the graveyard orbit.
And about how long would it take?
That's a great question. So simulations from previous research show that it will take a couple months to actually get it from GEO into the graveyard orbit. But my recent paper shows that we can, with the right technology, shows that we can increase the forces by actually pulsing the electron beam, which under optimal conditions can make it only take around like 5 days, which is a really cool finding.
Yeah, that's interesting. And then where are you getting your electrons from?
Yeah, so the electrons are coming from an electron gun, which works by applying a very strong electric field to a very small emitting tip. And then it launches the electrons from the
Right.
servicer spacecraft to the target.
But are the electrons a consumable resource on the spacecraft? Like you're pulling them from the spacecraft, I guess, and then firing them off, and so you're losing your electrons. Do you run out of electrons eventually?
Well, not really. So what happens is the spacecraft charges positive and the target charges negative. So eventually they reach a point where the electrons can no longer hit the target and they end up coming back to the servicer. And the net current on the spacecraft end up being zero. So it's not really a consumable resource, but like there is a stopping point. You can't charge infinitely forever.
But then will you get to a place where you will acquire more resources just from the solar wind? Like I'm just trying to think, like you've charged up that one satellite and now you're no longer connected to it. do you have to
Yeah.
get more electrons?
So the ambient plasma environment, like I said, so plasma is charged particles. And so the ambient plasma environment also causes charging on the spacecraft. So one challenge that I am really interested in my research is actually seeing how that ambient plasma environment affects the charging of both spacecraft, but really specifically the target spacecraft. Um,
Right.
yeah, because so Geo is very high up, like I said, and it feels a lot of the effects of um, solar activity and geomagnetic activity, and all of that changes the plasma populations. So that can affect how the spacecraft charges.
And then obviously you're going to need some kind of propellant on the ship that has the tractor beam. What do you call
Yeah.
it? The attractor? What do you call
The
is it
servicer
the
spacecraft.
servicer? Yeah. Okay. So you're going to need some kind of propulsion system on the servicer. So I'm assuming you probably want like an ion engine on it.
Yeah, that's honestly out of my wheelhouse.
Yeah.
I don't know too much about different types of electric propulsion, but it definitely would be a type of electric propulsion that could
Right.
thrust at small enough forces such that it doesn't run away from the target.
And can go after multiple spacecraft. Have you gotten a sense of like how many spacecraft you could service in this way?
Um, that would depend on the fuel capacity of the servicer. So again, it's a little bit out of my wheelhouse
Yeah.
when it comes to like the
Yeah.
design of the spacecraft, but
Yeah, no, I understand. But I like a lot of like people always ask me or my audience always says, why don't they just and then tell me what the idea is. And the why don't they just is why don't they just go and grab all the space debris that's up there and gather it up into some big ball somewhere that then future space explorers can use as a junkyard to build new spacecraft from. And I say, well, if you're going to try to match the velocity of the spacecraft, you're essentially spending an enormous amount of money. Every piece of spacecraft that is in orbit around the Earth is its own special butterfly. It's got its own velocity, its own direction. You've got to launch a multi-$100 million rocket plus satellite to grab one. And you've probably put up more space debris just by doing that. And so, a lot of the ideas that people are trying to propose for removing space debris is that it's just like how much debris can you process with one launch, with one spacecraft? And so it would be interesting to kind of just know, are you 5 days of firing your electric propulsion system, these things can run for years. So that actually feels like you could go after a lot of junk with one.
so that is the purpose of optimizing the speed because this is a geo mission theoretically, and so that is expensive, and we would, in order to make it worth it, like you said, it would be important to be able to reorbit as many satellites as possible during that time, while also making sure that the servicer spacecraft ends up in the graveyard orbit at the end of its lifetime.
Yeah, otherwise it'll just add to the space junk. But you
Exactly.
can kind of envision this future where you've got some of these servicers just there with some excess capacity waiting, and then when a spacecraft is out of fuel and it's time to wrap it up, you can then show up and for a fee or whatever, move it to its final home. So, I mean, this idea of charging your target one way and then that causes the spacecraft to be charged in the inverse. Are there other applications? Like you must look at this and go, I wonder what else we could do with this.
Yeah. So I think that the idea of what I'm going to call electrostatic actuation can be applied to a lot of different things. And the research that we do on the electrostatic tractor, beyond even just the electrostatic actuation part of it, is also something that can be applied to, I think, a lot of different topics. So the actuation specifically would be great for docking, proximity operations. It basically just increases the safety of these of these like close spacecraft operations.
Oh, that's interesting. Right. So you could have, say, these guns on the space station, and then as the spacecraft gets very close, then you just use their charge to pull them together as
Yeah,
opposed
like
to
rather than
using
using
thrusters.
very fine like thrusters, like fine movements on the thruster, which is kind of fuel expensive, you could then pull out the electron gun and use the electrostatic force to control your distance away from the spacecraft that you're trying to dock with or manufacture with, and but also, like I said, a lot of the other research that we do regarding the electrostatic tractor, I think, is important. So coming back to docking again, a lot of people in my lab, the AVS lab at CU Boulder, they look at touchless charge sensing. And that for the electrostatic tractor, that's important because we need to know what the potentials are, like to what voltage each spacecraft is charged to without actually touching it. And so for docking, that's important too, because there are simulations that show different spacecrafts being charged to very different potentials before they touch. And then when they touch, it causes arcing, which is a very sudden discharge that can be extremely damaging to both spacecraft. So that research has lots of applications as well, even without actually trying to move another object.
Are there any other forces that are on the target spacecraft? I mean, you've got the force that is pulling them together, but is there any other torques going on, any kind of rotation that would also come into play?
Yeah, so debris objects don't have any sort of attitude control. And so that causes them to just tumble randomly and wildly. And so that movement itself can actually cause fragmentation from the force, like from the centrifugal forces that are happening. And so when we use the electrostatic tractor, not only is there a pulling force, but there's also an additional torque. And so the torque can also be used for detumbling.
Mm. Right. So you don't necessarily need to move it to a graveyard orbit, although that would be ideal. But even just getting close enough, removing the tumble from it will make it a much safer object you could then deal with later. And it's not going to tear itself apart.
Definitely. It
Yeah.
definitely makes it a safer object, but I still advocate for fully removing these objects because they take up space in our orbits. And um, ultimately, I think even if you do detumble it, they can resume their tumbling after you stop putting a force on it. So I think ultimately that's the best solution, is to remove defunct spacecraft from their orbits.
And you were specifically looking at this at Geo, but do you see applications at Leo? Could you, I don't know, lower the orbit of the spacecraft enough that maybe you can knock a couple of years off of its deorbiting time, and then your servicer could raise its orbit again?
The reason that we've done most of our research in Geo and not in Leo is because um, the ambient plasma environment in Geo is much less dense, and that causes the electrostatic force to persist over many, many meters, can be up to hundreds of meters. Whereas in Leo, the plasma environment is extremely dense. So the electrostatic force would only persist over a few centimeters.
Oh, wow.
Yeah. And so, but it's a great question because when we think about orbital debris, we do think of Leo first. That's where we have most of our objects, most of the debris lives there. And so, one thing that we've been looking at very recently is what happens if we use electrostatic actuation in the wake of the servicer. So, when a spacecraft moves through plasma, dense plasma especially, it's like a boat moving through water, and it creates a wake behind it. And the wake is depleted of ions and electrons, but mostly ions, because in Leo, the thermal velocity of the ions is less than the orbital speed of the spacecraft. So that causes ions to only be on the RAM side of the spacecraft. So there's a wake behind it. And the wake has conditions that are more similar to GEO. The electrons are less dense and the ions are almost not there at all. And so perhaps we could also charge objects that are in the wake. That's something that's new, and there aren't publications on that yet. But it is an exciting project, and it would be great to be able to apply this electrostatic tractor concept and the electrostatic actuation concept in Leo.
Yeah, I, I'm, I think you're exactly right that a lot of people are most concerned with Leo because that's where all of these satellites are getting deployed, all these mega constellations. But these things are burning up all the time. Like the natural process is that this low orbit just cleans itself up within several years. The stuff that I really worry about is the stuff that's in the 1,000 to 2,000 kilometer range, because these things will last for hundreds, thousands of years. I mean, I know at GEO, then these things are lasting practically for millions of years. But so how does that plasma gradient change from, is it better at sort of mid orbits?
It's better at mid orbits, but it's still very dense, and it's hard to charge until you're much higher up.
So what about like asteroid mining? Could you go and retrieve an asteroid with your tractor beam?
Theoretically, maybe. You would need the right technology. So asteroids are pretty big, and bigger objects charge much slower. And so if you have a extremely large object and you're a tiny CubeSat servicer, you're going to finish charging way before, like, you're going to reach equilibrium way before this other spacecraft does.
I see. So you kind of really want the target to be of similar mass, or within a few orders of magnitude of the servicer, as opposed to something that is, say, 1,000 tons compared to your CubeSat.
That would be ideal. But of course, that's not always the case, especially because we do look at geosatellites, which are pretty large. And if we would want a mission that could do lots of different spacecraft, we would need a smaller spacecraft. So there's other research going on right now. I actually have an undergraduate student that is doing some research on this. And he's looking at what would happen if you attached an ion gun to the servicer spacecraft. So that way the servicer spacecraft could maintain an ideal level of charging while the larger object charges up. So yeah, ideally, someday we could do huge, like really big objects. We would need really high currents for that, and maybe, simultaneous ion gun charging. But it's something that we've thought about and that we're looking at.
I mean, there are asteroid mining companies right now that are thinking about like deploying a Kevlar bag to grab an asteroid that is of some size, say a 5-meter asteroid, and then you would drag it back to, say, the Earth Moon L2 Lagrange point, and then just pile a bunch of them up for use in harvesting various resources from them from space. And it'd be interesting to just like save the bag, just shoot the beam and be able to drag an asteroid behind you.
Yeah,
like a dog on a leash.
I think that would be really cool. It would also depend on like the material of the asteroid. It would have to be conductive so that it can charge.
Yeah.
But yeah, I mean, I think that there are probably a lot of applications that I haven't even thought of for this research. And that's what makes research so exciting.
Yeah. Yeah. Well, I mean, and of course you've got Star Trek as your guideline of what is theoretically, practically possible, right? So as long as like, have we got a tractor beam yet? No? Okay. Well, then let's keep working on it. Well, Amy, what are you obsessed with right now?
Well, I mean, I'm really obsessed with my idea that I've just talked about a little bit. These plasma signatures around the moon. I've brought it up to a few people and they're like, maybe could work. But I think that being able to characterize and document objects in space is extremely important. And, I really hope that we can continue to do really awesome science in space, and the debris problem will prevent that if there isn't more done about it. So I think that all the science that goes into it is really important.
But I would love to sort of understand your thought process, just because you're reading various technical papers, you're thinking about other people's work, you're focused on what you're doing as your sort of regular work. How does this stuff kind of percolate into your mind? Where you get these sort of random thoughts. You read something, you're like, I wonder if that could be used over here for this.
That's exactly what happens.
Yeah.
I it's hard to answer that question because it is just kind of an idea popping up. I stumble across a paper while I'm looking for a paper about something else. I read the abstract. I'm like, cool. And then, I put it on the back burner and I just think about it for a while. And this particular idea, we were talking about um, uh, grant applications, and I was like, I read this paper about using plasma signatures to detect objects in Leo. And then I have a colleague who just defended her PhD, and her PhD was all about using the electrostatic tractor in cislunar space. And she was like, actually, detecting objects in cislunar space is a really hot topic right now, and it's very important. And so from there, I, start looking things up, doing some Googling, and just sitting with it. And so, my current project is detecting those plasma signatures in Leo, but eventually I would love to start applying what I've learned from that project, because it's all very new to me. And applying it to cislunar space and seeing if it's possible in cislunar space the same way that we think that it's possible to do in Leo.
Yeah. Yeah. I mean, for me, I find it's like if the ideas just won't leave my brain, like the idea will pop up and I'll be like, okay, fine. Yeah. Take a seat. We can wait in line. And then a week later, I'll be still thinking about it and still thinking about it. And I'm sure that process is like, you're trying to think of reasons why it's a terrible idea. And it has survived all of your attempts to kind of discredit it in your mind. And then you're like, maybe. And then you have to figure out, how am I going to find the time to actually build this thing, investigate this thing, research this thing, and so on. It sounds like a NIAC application might be in order for you to send this on to NASA. Very cool.
Yeah.
It's a fun process, and unfortunately it never gets any better. Like the ideas just keep coming, and you just have to.
That is what I love about doing research. And I've been so lucky that my advisor gives us a lot of autonomy over what we do. And so it's such a fun process, like you said, to come up with an idea and think about the idea and then start looking into the idea. And and I really do hope, occasionally there are, roadblocks and challenges, but being able to solve a research problem, and, write a paper about it and share with the world my findings and even just my ideas like here is really great. And I love being a PhD student.
Yeah. Until you have to defend. That'll come.
I mean, that just means the journey's over.
Yeah. Well, Amy, thanks so much for taking the time to chat. Good luck with your research. I look forward to the Star Trek tractor beams.
Thank you. Yeah, me too.
I hope you enjoyed this conversation with Amy Haft. Now, we had a longer conversation about her other research specialization that's really interesting. And the idea is that there is space debris that is too small to detect optically, but as this material is moving around in low Earth orbit, it is going to be leaving a wake in the plasma around the Earth, and that theoretically this could be detectable and another way to track space debris. Now, this idea has been around in the literature, but Amy is thinking about how this could be applied into lunar orbit. As we have more and more spacecraft attempting landings on the moon, there's going to be space debris around the moon. How can we detect it? As always, we've got that longer interview over on Patreon, which, there's no ads. It's completely free. You don't have to sign up, don't have to donate. You can just go and watch it over there. But we're trying to encourage you to watch things over on Patreon. And this is why we do this. So check that interview out. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bielak, Dark Finger, Dave Giltonen, David Matz, Evan.pro, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Ren Kaidig, Richard Williams, Sean Sargent, Stephen Foundland-Munley, Team 49, Telescopes Canada, Vlad Shepelin, Wolfgang Klotz, and Zeldemort Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So this is great, right? When my love of science fiction runs into my day job of trying to explain various ideas in space exploration, we get this sort of perfect world. And it is funny how these ideas start out in science fiction, and I think they capture the imagination of not only audiences like me who just enjoy this stuff from afar, but also like potential scientists who then work their way up and to say, I'm going to build this stuff in real life. And a lot of the interesting technology has these roots. And so I think for the current generation of people out there who are watching science fiction, thinking about the various ideas, there's great shows that you can watch. If you haven't already watched Star Trek, catch up. But then, of course, at the time that I'm shooting this, Project Hail Mary just opened up in theaters. And so there's a lot of great science in stuff like that. And if you're young and you're thinking about what research you're going to go into and these ideas are exciting and interesting to you, take them seriously. This could be your career path. The future needs more people who are trying to turn science fiction ideas into science reality. All right, we'll see you next time.